Final change of trim of 7 inches by the head. Note that this is a change of trim from the original trim. So what are the final drafts and the final trim? The initial forward draft was 15 feet. This was increased 4 inches by loading cargo to 15 feet 4 inches. It was further increased by half of the change of trim, or 3.5 inches, to 15 feet 7.5 inches. This is the final forward draft. The aft draft started at 13 feet and increased 4 inches due to added cargo, and decreased 3.5 inches due to change in trim, for a final draft of 13 feet and 1/2 inch. The mean of these two final drafts is 14 feet 4 inches, which agrees with our earlier finding for final mean draft and is a good check. Now, this type of problem is almost certain to appear on your license exam, so be sure to practice it until you are confident that you understand it completely. Well, we've covered quite a lot of material up to this point, so why don't we take a coffee break for 10 minutes or so. This will give you a chance to look over your notes and to relax a little bit. So far, in discussing stability, we have considered only transverse stability, which is the stability of the ship from port to starboard or side to side. Longitudinal stability is also of some concern to the mariner, but is not as critical as transverse stability because most vessels have a very high degree of longitudinal stability. What we mean when we talk about longitudinal stability is the longitudinal or fore and aft locations of B, center of buoyancy, G, center of gravity, and M, metacenter. When a vessel is inclined or tilted longitudinally, the longitudinal positions of G and B create a couple which tends to rotate the vessel back to its original trim. If G is shifted to G1, the vessel trims until B has shifted to point B1, where it is again under the center of gravity, G1, and the ship is once again in static equilibrium. The longitudinal metacenter, ML, is located by the intersection of the lines of force through B before and after a small inclination. As you can no doubt imagine, the GML, or longitudinal metacentric height, is very large. Longitudinal center of gravity, LCG, and longitudinal center of buoyancy, LCB, are measured in terms of distance, feet, forward and aft of a certain point on the vessel. This point may be the forward perpendicular, or it may be the after perpendicular, or some other point. The forward perpendicular is a line perpendicular to the baseline, intersecting the forward edge of the stem or bow at the designed waterline. The after perpendicular is found in the stern of the vessel, and its precise location will vary depending on the particular configuration of the stern of the vessel in question. On modern vessels, it usually passes through the rudder post. The frames on a ship are usually numbered from forward to aft, and frame number 0 can usually be found at the forward perpendicular. You should refer to the ship's plans to see which system was used on your vessel. One other type of problem that we frequently find on license exams is to solve for location of the longitudinal center of gravity, LCG. The procedure is similar to solving for vertical center of gravity, except that the reference point is the forward perpendicular instead of the keel. As an example, take an empty ship and then load on it the following weights: 80 tons, 90 feet forward of the after perpendicular; 45 tons, 210 feet forward of the after perpendicular; and 100 tons, 360 feet forward of the after perpendicular. Multiplying each weight by its distance from the after perpendicular, we obtain longitudinal moments of 7,200, 9,450, and 36,000 foot-tons, respectively. The sum of these three moments is 52,650 foot-tons. Dividing this by the total weight loaded, 225 tons, we get a figure of 234 feet FAP forward of the after perpendicular. This distance represents the point where the 225 tons of additional weight appears to act for purposes of calculating the trim of the ship. If the tipping center is more than 234 feet forward of the after perpendicular, the ship will trim by the stern. And if the tipping center is less than 234 feet from the after perpendicular, she will trim by the head. Actually, this is only a partial solution to our problem. In order to find the actual LCG of our vessel after loading, we must take into consideration the LCG of the vessel prior to the loading operation. Let's assume that the vessel we have been talking about had a displacement prior to loading of 7,000 tons, and its LCG, as determined from the hydrostatic curves, was 205 feet aft of the forward perpendicular. If the length between perpendiculars, or LBP, is 445 feet, and the original LCG was 205 feet aft of the forward perpendicular, well, this is the same thing as being 240 feet forward of the after perpendicular. The moments of the ship without her cargo are thus calculated by multiplying 240 feet times 7,000 tons, which gives us 1,680,000 foot-tons. This is added to the moments for the cargo, 52,650 foot-tons, to give us a total of 1,732,650 foot-tons. Now these total moments are then divided by the total weight, cargo plus ship, or 80 tons plus 45 tons plus 100 tons plus 7,000 tons, or a total of 7,225 tons. This will give us a final LCG after loading of 239.8 feet forward of the after perpendicular. At several points in this lesson, we have referred to two graphs called the deadweight scale and the hydrostatic curves. Now we'll take a look at these two graphs and we'll learn how to use them. The deadweight scale is usually included as part of the vessel's capacity plan. The scale is usually entered with the vessel's draft, and then it is possible to read across the scale and determine the MT1, deadweight, displacement, and TPI for that particular draft. As an example, let's examine the deadweight scale for the SEDCO 445. A reproduction appears on page 11 of the SEDCO Self-Study Guide. Besides the information just mentioned, you can see that the graph also shows us the light draft and displacement and the maximum summer load line, which you will notice is to the top of the line through the load line circle. The light draft is the draft with the ship completely empty, no cargo, crew, fuel, stores, or water on board. Deadweight at light draft equals 0. The light draft displacement is always the difference between deadweight and displacement at any other draft. Let's say we go aboard the SEDCO 445 in the process of loading. We want to know about how much cargo she has aboard and how much more we can load. While on the dock, we read the ship's draft as 25 feet aft and 21 feet forward. The mean draft is thus 23 feet. Once aboard, we find the capacity plan and locate the 23-foot mark on the deadweight scale. To the left of this mark, we see the deadweight column, and the deadweight amount corresponding to a 23-foot draft is 7,050 tons. What this really means is that there is slightly more than 7,000 tons, these are short tons, of fuel, water, stores, drill pipe, and so on board. At the top of this scale, on the line indicating the freeboard or maximum summer draft, we see the number 8538 in the deadweight column. Subtracting the deadweight for 23-foot draft, 7,050, from the maximum deadweight, 8,538, we get 1,488 tons, which is the amount of weight we can still load if it will fit. Now, this is about all you will have to know about the deadweight scale for purposes of the license examinations. The hydrostatic curves duplicate all of the information contained in the deadweight scale, plus a lot of other information. You will find a reproduction of the hydrostatic curves for the SEDCO 445 on page 12 of your SEDCO self-study guide. As you can see, the curves are in a graphical rather than a tabular form. Along both sides are draft scales. As with the deadweight scale, we usually enter this graph by first locating the desired draft along the side of the graph. Once we have found that point, we lay a straight edge until it intersects the curve that we are looking for. The graph contains curves for tons per inch immersion, height of longitudinal metacenter, vertical center of buoyancy, displacement in fresh water, salt water, MT1, change in displacement for trim by the stern, longitudinal center of flotation, longitudinal center of buoyancy, height of the transverse metacenter, and some additional information of a design nature. Once we have located the desired curve, we find the point where the applicable draft line intersects it. From that point, we proceed vertically up or down to the top or bottom margin of the graph. Here we may find two different scales depending on whose curves we're using. One type will have a separate scale for most of the curves. The other type will have a common scale for all with a different factor for each curve. If this is the case, you multiply this factor times the scale reading to obtain the correct figure for your draft reading. For example, if we want to locate the longitudinal center of buoyancy for a draft of 21 feet on the SEDCO 445, we find 21 feet on the right margin of the curves. Then we go along the 21-foot line until it crosses the longitudinal center of buoyancy curve. Now we move vertically downward from this intersection point until we find the LCB scale. On this scale, we read that the LCB is 213 feet 6 inches aft of frame 0. You should remember that frame 0 and the forward perpendicular are the same point on the vessel. Now, this procedure is the same for obtaining any other information contained on this graph. The last type of problem you may encounter on the license exam, and one that you may occasionally meet in the day-to-day operation of a rig, concerns the change in draft a vessel will experience in proceeding from fresh water into salt water, or the reverse. To understand these problems, you must understand the difference in density between salt and fresh water. Salt water is heavier than fresh water. If we fill two containers of exactly the same size, one with salt water and one with fresh, and if we weigh them, the one with the salt water will be 2.6% heavier than the freshwater container. What this means to us is that since salt water is denser, it takes less of it to buoy up or float a ship than the amount of fresh water the same ship would require. As a result, a ship will float higher in seawater than in fresh. This is the important point to remember. In passing from salt to fresh, or the reverse, the draft is always less in seawater. As an example, consider a vessel loaded to a 48-foot draft in fresh water. As she puts out to sea, will her draft change, and if so, in what amount? Since she is going from fresh to salt water, she will rise bodily to have a smaller draft. The formula for solving this problem is the draft in seawater is equal to 35 over 36 times the freshwater draft. So multiplying 48 feet freshwater draft by 35 and then dividing by 36, we get a result of 46 feet 8 inches, which is the seawater draft. The ship has changed draft by more than 1 foot. When bringing a rig into freshwater port, the draft will increase and caution may be called for. In this case, we simply reverse the formula to read the draft in freshwater is equal to 36 over 35 times the draft in salt water. This completes the subjects of the second lecture on stability and trim. Now let's take a few minutes to review some of the major points covered in this lecture. Displacement is the weight of water displaced by a floating object. It is equal to the weight of the object itself. Free surface effect occurs when a vessel has partially filled tanks. The effect is such that it causes a decrease in metacentric height, GM, and a consequent reduction in stability. The wider the tank, the greater the free surface effect. The greater the displacement of the vessel involved, the less the effect of free surface upon stability. The specific gravity of the liquid in question will also have an effect on the magnitude of the free surface effect. Rolling period is the number of seconds it takes a vessel to make a complete roll. That is, from starboard to port and back to starboard again. Remember how to solve for the rolling period of a vessel that has a ship-shape hull. Rolling period in seconds equals 0.44 times the beam divided by the square root of the metacentric height. Draft is the distance from the bottom of the keel to the waterline. It is measured in feet and inches. Draft marks are found on both sides of a vessel at the bow and at the stern. Trim is the difference in the drafts fore and aft. Change of trim is the algebraic sum of the initial trim and the final trim. The tipping center, or center of flotation, is the point around which a vessel trims. The MT1, or moments to trim 1 inch, is the number of moments, measured in foot-tons, necessary to change the trim of the vessel 1 inch. The TPI, or tons per inch immersion, is the number of tons necessary to change the mean draft of a vessel 1 inch. In solving problems where cargo is loaded or discharged, first determine the mean draft, and then enter the deadweight scale or hydrostatic curves and determine the TPI. Secondly, divide the total weights loaded or discharged by the TPI to determine the effect upon mean draft. Next, using the new mean draft, enter the hydrostatic curves or deadweight scale to get the MT1. Then calculate the net moments for the increased or decreased load and divide by the MT1 to get the change of trim. The change of trim is then applied 1/2 at the bow and 1/2 at the stern to determine the final forward draft and the final after draft. Longitudinal stability is involved with the fore and aft locations of the center of buoyancy, LCB, and the center of gravity, LCG, and the metacenter, ML. The forward perpendicular is a line perpendicular to the baseline, intersecting the forward edge of the stem or bow at the designed waterline. The after perpendicular is found in the stern of the vessel. It usually passes through the rudder post. Frame number 0 is usually found at the forward perpendicular. In order to solve for the longitudinal center of gravity, or LCG, we use the theory of moments. We find the LCG for a vessel after loading and or discharging by dividing the total longitudinal moments of the ship and her cargo by the final weight. Remember that the moments for the vessel are found by multiplying the displacement before loading or discharging by the distance the LCG for the mean draft in question is located from whichever one of the perpendiculars we are using as a reference point. When a vessel goes from salt water to fresh, or vice versa, the draft is always less in seawater. The formula to remember is draft in salt water equals 35 over 36 times draft in fresh water.